Welcome back. In this lecture, we will talk about resistor impedance. Impedance can be expressed in dB ohm. This is the basic unit for impedance in AC analysis. This becomes very helpful when capacitors and inductors are considered in the circuit analysis. Also, dB ohm is the fundamental of passive filter design. The magnitude of an impedance Z can be expressed in dB ohm. Just as dB or decibel as we introduced before. Here we introduce our base. This is the base resistance, which is 1 ohm. For example, in this table we have the actual impedance in decimal. Unit is ohm. On the right column we have impedance magnitude in decibel ohm or dB ohm. You may notice that this table has the same magnitude as before. The only difference is the unit, which is dB ohm. Now let's use LT-spice AC analysis to find the impedance of a resistor over frequency. So this is the basic setup in LT-spice for AC analysis. In the top left corner of the slide, you can see the schematic of the AC analysis. If we right-click over this current source, we have a small signal AC analysis. The AC amplitude is 1, which means 1 amp. If you right-click over this syntax .ac, that means the AC analysis. This window will pop up, and you can see the AC analysis settings. The type of sweep is by decade. The number of points per decade is 10 in this case. We start at 1 Hz and stop at 1 MHz. This is the syntax for the AC analysis command. And if we click OK, we can run the simulation. Now let's calculate the resistance in dB ohm. Here we have 100 ohm. Based on this equation, we have 40 dB ohm. Since the AC magnitude is 1 amp, we expect to see the voltage over R1 equals to be 1 amp times 100 ohm, which is 100 volt. 100 volt equals to 40 dB. Let's run the simulation in AC analysis. If we click the voltage across the resistor, we can see the magnitude is 40 dB, which is 100 in decimal. You can see the x-axis is the frequency from 1 Hz all the way up to 1 MHz. The impedance is 40 dB, and this is why. As I explained before, since the current magnitude is 1 amp, the voltage over R1 has the same magnitude as its impedance. So now let's double check the impedance over R1 by using the voltage divided by the current through the I1. As a result, the impedance is found as 40 dB ohm, which is the same as before. In this example, we change the AC current magnitude to 0.1. We have the same circuitry as before. This is the only change. So two questions for you. What will be the voltage across R1 in dB? The second question is, what will be the resistance R1 in dB ohm? You can pause this video and think about these two questions. So this is schematic. The only change is AC current magnitude is changed from 1 to 0.1. Since the voltage equals to 0.1 times 100 ohm, which is 10 volt, which is equivalent to 20 dB. Since we still have 100 ohm in this case, this is 40 dB ohm, which is the same as before. This is the AC analysis results. The voltage is reduced to 20 dB because the AC magnitude is changed to 0.1, which is minus 20 dB. In this case, 40 dB, which is 40 dB ohm, minus 20 dB equals 20 dB in voltage. If we calculate the resistance over R1, by using voltage over current, we can see the impedance is still 40 dB over 1 Hz to 1 MHz frequency range. A quick overview for this lecture. In this lecture, we talk about magnitude of an impedance Z or impedance R in dB ohm. This is an important concept in this course for AC domain analysis. We did some simulation in LT-SPICE using AC analysis to find the impedance over a resistor. Remember to run some simulation on your own to gain some hands-on experience. Thank you and see you next time.